Hello, is it on? So actually, some visitors were coming, mostly related to number theory, at this more or less at the same time. So it was decided that we have some small workshop, and so some people from here, local includes Vidya Mandir, one colleague, and some from here, or students, postdocs, and teachers, and then visitors. So with that, that's a mini workshop. And this is something it will be, I requested people to keep it level so that students get something and then they will see in what type of research happens and what. Because in the classroom lectures are different than this. So this is some opportunity for them. So with this, I request, okay, today Professor Ilangovan to chair today's session.
So first let me welcome all of you. It's the first day of the workshop and it's good to see already some of my old friends who have come here. And it's nice that today when I am chairing the session, I have one current colleague and one ex-colleague giving talks. So first I welcome Professor Stephen Bayer, one of my esteemed colleagues. Your talk on Brun-Minkowski inequality, and first year students be happy. These things are going to come in exam, he has promised.
Okay, so I continue with measure theory. In fact, I built a bridge between additive combinatorics and measure theory. About additive combinatorics, I don't know much. What I know that I know from talks, basically. I do analytic number theory. Not worked on additive combinatorics. But okay, so let's say some things on typical problems in additive combinatorics. One important circle of problems is sum sets. So you take two finite sets of the integers a and b, and you form the set of all sums a plus b, where a belongs to capital A, b belongs to capital A. So the interesting question is, what can we say about the cardinality of a subset? I give some examples, very simple examples, which show some extreme cases. So let's also focus on the case when A is equal to B. This is particularly interesting. Then we write A plus B. That's not. Here. Is that okay? A bit too loud? Okay. Huh? Oh, okay. Oh, like that. Yeah, so that is much better, but it's still not optimal. Yeah. So, okay, yeah. Good, so A plus B, where B is equal to A. Denoted as 2A. So we just form all sums of elements of sets. Sums with two summands. So then there are two extreme examples. Let's look at the set 0, 1 up to n. So then the sum set is simply set of all integers between 0 and 2n. So what can you say about the connection of the cardinality of 2a and cardinality of a? you find the cardinality of 2a is 2 times cardinality of a minus 1. That is best possible. So that's the lowest which you can get. In fact. So then an example when you have large cardinality, let's look at a geometric progression. So all the powers of 2 of the form 2 to the 0, 2 to the 1, up to 2 to the n. So then, since binary expansions are unique, every element of the subset is represented at most 2 times in the form 2 to the I plus 2 to the j, or 2 to the j plus 2 to the I, where a and j belong to the set 0 to n. And of course, the diagonal 2 to the I plus 2 to the I, that's represented on the ones. That's also best possible. In the sense that's the largest possible cardinality. And what you get is, you can easily calculate. It is cardinality of a plus 1, choose 2. So in fact, in the first example, it's just by a factor 2 of the cardinality of a. In the second example, it's almost the square of the cardinality of a factor times the square of cardinality of a. Okay, so there are some deep results in additive combinatorics on when the cardinality is small, when it is large. So very vaguely, it can be summarized as follows. If we have a lot of additive structure, then the sum set turns out to be small. In the other case, when we have a lot of multiplicative structure, as we have seen in this example, the cardinality tends to be large. So there's Feynman's theorem, for example. I will not state that here. It's not a talk about additive combinatorics, in fact, but I make the bridge to measure theory. Okay. Of course, we can generalize these questions easily. Let's look, instead of z, let's look at z to the d. Or let's look more generally on subsets of abelian groups. And you can also take finite abelian groups. The question remains interesting. Let's stick to AB subset of C to the D. What we may have in mind here is just the subset of C square, Z square, to keep things simple. But we formulate the following for subsets of Z to the D in general. So now the cardinalities of A, B, and A plus B can be rephrased in terms of Lebesgue measures of certain sets. You can have in mind subset of Z square. Similarly, for subsets of R to the D, we define the sum set C plus D, consisting of all sums of elements of C and elements of D. That's called Minkowski sum in this setting. So now you can actually rewrite the cardinalities of the subset A, the subset B of Z to the D as follows. Maybe I should draw something. It's a bit little color. So I draw Z square. So these are these points in Z square, these lattice points. Okay, and let's say A consists of 2 points, that point, that point. So now what you are doing is you add a square with side length 1/2, open square, a half open square, like that. And here again, a half open square, like that. So then, of course, when you look at the Lebesgue measure, since these squares are disjoint, Lebesgue measure of the resulting set A tilde, so the union of these two squares is A tilde, is nothing else than cardinality of A divided by 4 in that case. In general, divided by 2 to the t. Okay, and you can do the same with the set B. Let's take just one point. That point. So then you add this half open square. And now what happens when you take the Minkowski sum of these two sets? In fact, it turns out to be the sum of A and B, subsets of Z square, plus a full unit cube. Because the sum, Minkowski sum, of two half cubes is precisely a unit cube. So what you get is, in this case, these 2 points. So the sum set consists of, a number of points. A plus B. So that plus that, that plus that. In this case, only 2 points. But looking at A tilde plus B tilde, you get that set here. Okay. The disjoint union of two half-open cubes of side length 1. So in this case, cardinality of A plus B is exactly the measure, Lebesgue measure of A tilde plus B tilde. So that means you can rephrase some sets of Z to the D and their cardinalities in terms of measures of suitable subsets of R to the D. All right. So now I have reached subsets of R to the D, and the rest of the talk is about what can be said about Minkowski sums of subsets of R to the D. So the natural question arises, what can be said about the Lebesgue measure? So now let me make a couple of remarks before I come to the actual inequality, which I want to prove in this talk. The Brunn-Minkowski inequality. First of all, it should be remarked, so we certainly want to deal with measurable sets. If A and B are measurable, it does not need to be the case that A plus B is measurable. For example, take that example. You take a non-measurable set in R, take the Cartesian product with a point 0, and on the other hand, you take also product of the point 0 with a, let's say, an interval. You can just take an interval. So then what happens if you add these two sets? The measure theory students think of the Vitali set, which we discussed in quite some detail. So that's this. So now the Vitali set, we can put it in an interval 0, 1, for example. Think of it like a set of points here. And we take the Cartesian product with 0. That means it will be contained in that line segment. On the other hand, B will be a line segment joining 0 and 1. So then the sum set will be nothing else than consisting of these line segments here. So it can be easily seen that that set is also non-measurable. However, A and B are 0 sets, so they are measurable. We know from measure theory they are measurable. So it does not need to be the case that A plus B is measurable if A and B are measurable. So let us from now assume that all these sets are measurable. A plus B is also measurable. All right. Yeah. Good. So now I make a review. That's why I said what I talked today about is related to the midterm exam, but the previous exam, which we already conducted. So there are some interesting results from the midterm exam, which I put as problems, sometimes with some hints. Also, interestingly, if one of A and B is not measurable, it can be the case that the sum is measurable. Let's, for example, look at the Vitali set. So that picks out from, so let's consider this quotient group of the additive group R, quotient additive group Q. Then the Vitali set picks out from every coset of Q precisely one element. So now, then what happens if you add V and Q? What you get is precisely you get R. So that is the one question which actually tricked a lot of students, but some actually got it right. So this is a measurable set. Okay, but that's not that important. What I want to discuss is the measure of A plus B. First of all, things are easy if one of these sets is countable. So then if A is measurable, B is countable, then A plus B is countable. The reason being that we can write it as a countable union of measurable sets. So then, yeah, so we dealt with one very simple case when A is measurable, B is finite. So then we easily find by writing as a union this inequality. Also, if A is a zero set, B is countable, then A plus B remains a zero set. Also, again, writing using a countable union of zero sets and then using subadditivity. But so now comes the interesting thing. If A is a zero set and B is a zero set, it doesn't mean automatically that A plus B is a zero set. It's the case if B is countable, but if they are both not countable, uncountable, then it can happen that actually the sum is a non-zero set. And so the example which I put on the axiom is we take the usual Cantor set and we take half of the Cantor set. Then, so A consists of all numbers between 0 and 1 with ternary expansion, which contains only 0 and 2. A half contains ternary numbers with digits 0 and 1. So you can write every element of the interval 0, 1 as a sum of these two. So the interval from 0 to 1 is contained in the sum. That shows A plus B is not a zero set, whereas A and B are both zero sets. That's quite surprising. And similarly, if you take sets of finite measure, the sum does not need to be a finite measure. Even we can take one of these sets to be zero, a zero set. Let's take A equals Z and B the unit interval from 0 to 1. Then the sum set will be, okay, that is 0 plus this interval, then 1 plus this interval, 2 plus this interval, and so on and so forth, minus 1. So you will get whole of R. So that's the largest possible, but these two sets are just small. So this shows that actually M A plus B can be rather large. So we have not good upper bounds for that unless we have special situations. But on the contrary, we may hope for good lower bounds. That is the content of the Brunn-Minkowski inequality. Okay, so to motivate that, let's look at some example where we have good control of the cardinality of A plus B. That's actually the case if A is a convex set and B is a scaling of that set. So you take, for example, a circle, let's say. You take a circle. That's a convex set with any 2 points. The line segment joining these 2 points is also contained. And you take a scaling, lambda A. If lambda is less than 1, that will be a small circle. So then you form the sum set. And the claim is you get actually the set 1 plus lambda A. That means these two circles add to a larger circle. A circle like that here. Radius 1, radius lambda, let's say. Radius 1 plus lambda. The reason for that is, okay, let's see the two inclusions. 1 plus lambda A is contained in A plus B. So every element of 1 plus lambda A will be of the form 1 plus lambda little a. Clearly that is contained in the subset. A plus lambda A is element of A plus B. But the converse also holds. That's an interesting thing. Take an element of the sum set that will look like, so A1 plus lambda A2. But you can write it in that form. Pull out a factor of 1 plus lambda. Then you get it as that. And this point lies on the line segment joining A1 and A2, which we know is also contained in A. So altogether, this will be contained in 1 plus lambda A. So we have that conclusion. So that's a very nice thing. In that case, let's look at the measures of these sets. MA plus B. So we now take the power 1 divided by D, in this case, square root of these two things. A plus B, measure of that is measure of A times 1 plus lambda square, or in general to the D. So if you take these roots, you get 1 plus lambda M A to the 1 divided by D is equal to MA to the 1 divided by D plus, and this set B, that's this set, that is measure lambda square, measure A. So when you take square root, you get lambda times MA. So this inequality, this equation holds in this case, interestingly. And so now what does Brunn-Minkowski say? Famous inequality. So now I come to the what I actually want to talk about. This says that we have always an inequality of that form. So the left-hand side is always greater or equal to the right-hand side. Yeah, so this example shows that this inequality is actually sharp. So in the context of R to the D, we get this nice inequality. Yeah, so again, I made some philosophical nonsense remark here. You can ignore it, but so we also can say that actually a convex set contains has a lot of additive structure. Because when you take any 2 points, then the part of the affine subspace joining these two is contained in the set as well. But okay, you forget about that. Yeah, so how to prove that? So that's a usual measure theory proof, or we can prove it by a usual measure theory procedure. We start with very simple sets. Usually one starts with rectangles, and then one goes up to more complex sets, and so on and so forth. So let's just see what happens if we take rectangles, put it in a d-dimensional space. Dimensions of these rectangles are A1 times A2 times A to the D, side lengths, and B1 times B2, and so on up to B2, BD. So then A plus B is a rectangle. Clearly, the dimension of that will be A1 plus B1, cross, and so on up to AD plus BD. Okay, maybe I draw here a sketch of that. Think of two-dimensional rectangles. So one rectangle, another rectangle, and then you will get a rectangle like that here. So. That is A1, A2, B1, B2, A1 plus B1, A2 plus B2. And the nice thing is you can shift the rectangles as you want. It still remains the same dimension of the subset. Okay, so how does the Brunn-Minkowski inequality look like? So the measure is nothing else than the product of the side lengths. you take these roots and get this inequality. So that is what needs to be proved. But that's a very easy exercise. So first of all, observe that we can make all these equal to 1. So when we multiply ai and bi simultaneously with the same lambda I, then the right-hand side will expand by a factor of lambda I to the 1 divided by d, and the left-hand side as well. So it is homogeneous, that whole thing. So that means without loss of generality, we can assume all these sums to be 1 here. So I wrote that here. Yeah, so what happens then? Then 1 will be the arithmetic mean of these things. We can divide it into 2 parts. And then we just use the arithmetic mean, geometric mean inequality. And we get that inequality. And we are done already. So very quick proof. The tricky part comes when we go to the next stage. We consider finite unions of rectangles. So we say A is a finite union of rectangles, B is a finite union of rectangles, and we assume they are almost disjoint. So that means we have a situation like that. So I have 2 colors, this is good. So we have here rectangles, they are allowed to be almost disjoint. That means they may join in a face, but not overlap properly. So maybe one more rectangle, then set B. So that can also overlap with the set A, is allowed. But the rectangles in B which make up B need to be almost disjoint as well, something like that. So we want to prove that then also Brunn-Minkowski works. So what we do is we do induction over the total number of rectangles making up A and B. So that means in this case, number of rectangles is equal to rectangles equal to 6. So the base case, if you have 1 rectangle, then there's nothing to be proved. If you have 2 rectangles, then that's exactly what we have proved. So base case is n equals 2. Base case n equals 2. So we want to do induction over n with that base case. Okay. Yeah, so now the important observation comes, which I mentioned already before. If we shift the sets A and B by any parameters, any elements of R to D, we get just a shift of the sum set. And then, since the Lebesgue measure is translation invariance, the measures remain the same as before. So we are free to shift A and we are free to shift B as we like. So now what are we doing is the following, and that's a bit tricky. So we do a reduction from n to n minus 1 rectangles. So that we do by, in fact, dividing A into 2 sets after making a suitable shift. So the shift which we are making is in such a way that we get 2 rectangles which are separated by, so let's look at the 2-dimensional case here, separated by the x or the y-axis. That's always possible. So let's say, for example, here in that example which I drew, so that's the x-axis. Then shift the set A, so these 3 rectangles make up the set A. Shift it down. Then, for example, these 2 rectangles can be separated by the x-axis. So this is R1, R2, and this shifts down here. There may be another rectangle, let's say like here. That is also belonging to the set A. That will be divided by the x-axis. If that's not possible, we can shift it in such a way that it's separated by the y-axis. So let's assume it's separated by the x-axis. And then let's see what happens if we take this set. So now the new set A intersected with the upper half plane, and the new set A intersected with the lower half plane. What we see is that we get one rectangle less at most. So it can be even smaller number. So let's count here. So A intersection the upper half plane and A intersection the lower half plane. So this is one rectangle, another rectangle, and this is another rectangle. In this case, this rectangle is divided into two parts. We started with 4 rectangles. We get now 3 rectangles. So then, so this is set A minus. This is set A plus. So A plus, how many does it have? 1 rectangle and a second rectangle. So this rectangle and the second rectangle. So let's keep in mind the important point is we now get 2 sets which have 1 less rectangle. So then I wrote that on the slides here. So then we can do the same actually for the set B, but we don't insist on separating any rectangles. But what we do is, so that the calculation which we do next works, we fine-tune our shift in such a way that actually ratio of M measure A plus and MA is the same as the ratio of MB plus and MB. Then automatically this holds also for MA minus divided by MA is equal to MB minus divided by MB. Because A is the almost disjoint union of A plus and A minus, so we have this equation, and we have the corresponding equation for B. So we can produce a shift of the set B in such a way that we produce 2 sets B plus, B minus, satisfying this equation. Okay. So now comes the calculation. So first of all, we make an inequality. We observe that A plus B contains the set A plus B plus union A minus plus B minus. The good thing is that A plus B plus lies in the upper half plane, whereas A minus plus B minus lies in the lower half plane. And now we can use the induction hypothesis because A plus and B plus together are made up of at most n minus 1 rectangles, and A minus and B minus together are made up of at most n minus 1 rectangles as well. If n is the number of rectangles A and B together are made up. So now we can apply induction hypothesis, which we are doing. So trivially, just by monotonicity, we get, and by additivity, we get measure of A plus B is greater or equal this measure in the second line. So now we can use the Brunn-Minkowski inequality for n minus 1. So that means for the sets A plus B plus and A minus plus B minus. And now the third step reveals why we shifted B in this clever way. If you apply that, easy to see, you will get this representation here. Yeah, so that, yeah, okay, it's easy to see. Yeah, if you multiply MA plus with that side, what you get is this, applying this ratio equation. And if you multiply that with that, you get that here. In fact, it's an equation, it's not an inequality. Good, so then these two measures together give that, and then just multiplying that with that gives that. And you are done with the Brunn-Minkowski inequality. Yeah, miraculously. So now when we have finite unions of rectangles, then the rest is easy because we know how we approximate more complicated sets in measure theory. I just wrote that as a sketch. So we know from measure theory every open subset of R to the D can be represented as an almost disjoint union of rectangles. The union is countable. That I should write. Okay, I need to write countable union. That I forgot on the slide. That's very important, of course. Otherwise, it would be meaningless. So therefore, you can approximate every open set arbitrarily closely from inside by a finite almost disjoint union of closed rectangles. So by the way, I always want to assume that the rectangles are closed. I didn't say that here. Then we can turn to compact sets. We know also from measure theory we can approximate them from outside arbitrarily closely by open set. And finally, you can approximate every measurable set of finite measure arbitrarily closely by compact sets. So then, making that precise, you get the Brunn-Minkowski inequality in general. So now, question is how much time I still have? Yeah, I still have enough time to present one important application of that. So that has now really nothing to do with additive combinatorics, but okay, let's just demonstrate that this gives something interesting. Or it has actually several applications. So one is the isoperimetric inequality. So what this says is, so when you take any rectifiable, simple closed curve, then the curve for which the maximum area enclosed is achieved is the circle. So take a curve, you can arrange that as a square or you can arrange that as a pentagon or whatever, or a curve like that. It turns out you get the maximum area if it is a circle. Intuitively very clear, but it took a long time to prove that actually precisely. There were proofs which turned out to be faulty. So using Brunn-Minkowski inequality, one can prove that rigorously. But I will use some things in that proof, which I will not establish. Yeah, so let's formulate it first as a theorem. So we take omega, a bounded open set of R square with boundary. So that's the boundary here. Being a rectifiable curve, that means the arc length of the curve is finite. So then the inequality says 4 pi measure, so the content of the open set omega is bounded by the square of the length of the curve. So let's see that this inequality is sharp, and actually we get equality if we take a disk. So if you take a disk of radius r, then the measure is pi r square, the area, and the arc length is 2 pi r. So then just plug this in, and you get equality. Exactly. Good. So we see the inequality is sharp. So yeah. So how is the proof? What is the proof? The proof is not difficult, in fact. So no, not yet. Come on. So now I remove that. So I should say I should draw what these sets look like. Let's take a simply connected set for simplicity. But it works also for not simply connected sets. So like a set like that. That's our omega. Actually, I was tempted to draw a circle, but I don't want it to circle. So then omega plus delta that will be the set of all points which have distance to the closure less than delta. So that means it will look like that. So it will contain that set lambda. So this is lambda plus. And then lambda minus is the opposite. So we have distance to the complement of omega greater or equal delta. So that will be inside, yes. And then we have everything which is enclosed by these two curves. So the union of omega plus minus omega and omega minus omega minus. So that will be that set here. So this tube or kind of annulus thing or bicycle tire, whatever. So you can also write this difference between omega plus and omega minus in that form here. So every point which is in distance less than delta to the boundary of the original set. So the boundary is that blue curve here. So, okay, so this is, there should be some new pens actually. Gamma, okay, so gamma is equal to delta omega. No. So now you can, so let's say d delta is the open circle centered at the origin with radius delta. So then now we can observe that we can actually write omega plus, or we can say that omega plus contains omega plus this unit circle. So you just draw around every point a unit circle and then take the union. So let's consider at a boundary. Not unit circle, but circle of radius delta. So like that, and here that. And you can also take a point inside, and so on. And you take the union. That will be clearly contained in omega plus. Similarly, omega will contain omega minus delta plus the circle. Okay, so you get two subsets that way. And now you can use the Brunn-Minkowski inequality for this. So measure of omega plus is greater or equal that by Brunn-Minkowski inequality. So then for the circle you can easily calculate what you get. So this is this area. And then you throw away this, you multiply out the square and throw away one term, you get that. Okay, similarly, you do for the other inequality. So you get this inequality. Okay, you get the first line and then you shuffle around some terms. And then you add the two inequalities. So what you get is, remember that inequality and that inequality. If you add, then this term just cancels out. And you get this here. So now what happens if you make delta very small? So you make this tube smaller and smaller. So if it is a very nice smooth curve here, then if you take the limit delta tending to 0, measure of this set gamma delta, this should not be gamma delta. This tends to the length of gamma. That's not surprising. So imagine if you take the measure of this. So let's take a very thin tube like that. So the distance here is 2 delta. if you take the measure, divide that by 2 delta, then in the limit you should get actually length of that. Okay, so that does not hold in general. We can have very rough curves, but in general what we have is that, yeah, lim sub, so lim sub is less or equal to that here. Okay, so that you can establish easily. Yeah, so then take a limit on the left-hand side, divide by 2 delta both sides, take lim superior on both sides. So then you get length of the curve gamma is greater or equal lim sub delta tends to, 0. Oh, I forgot. I made a mistake. 0, sorry. I'm so sorry. Okay, you divide by 2 delta, then what remains is just pi n to the 1/2. And this here tends clearly to that. So on the right-hand side, you will get 2 pi to the 1/2 times m rho to the 1/2. And that's exactly the isoperimetric inequality. Okay, that's all. Thank you for your kind attention. So the midterm exam is good for something, apparently. Yeah. Yeah, because for the circle it's sharp. For the circle it's sharp? Ah, yeah, okay. And then we need to see for other it's not sharp. Yeah, that's right. That's not completely, yeah, that's right. Yes. Not immediately clear, yeah. Which application? Oh, who did that originally in that way? I don't know. I didn't check. Yeah. Yeah, so you can shift it. I mean, so so take the function. Take the original set B, made up of some rectangles or something. So then consider measure B plus divided by measure B. So now shift the set by a parameter t. So what you consider is, in fact, B plus t plus divided by measure of B. So you take some shift in the y direction. So that's a function of ft. So that function is continuous. It's a continuous function on R, certainly. So if you let t tend to infinity, then, so that's a shift in that direction. So you should write here, in fact, 0 t plus. So if you shift in far enough in the y direction, then all of these rectangles will lie in the upper half plane. So that means what you get is limit t tending to infinity, f of t is equal to 1. On the other hand, if you shift all the rectangles downwards, then at some point all the rectangles will lie in the lower half plane. So that means limit t tending to minus infinity, ft equal to 0. Now that's continuous, obviously. So take the mean value theorem. So you want MA plus divided by MA to be equal to FT. Just take a suitable T, you will achieve that ratio here. That will lie between 0 and 1. So that's all. Yeah. Hmm? Yeah, I know that place. Yeah, that will be automatically countable. You are completely right. Yes. Yeah, they have not. Okay, but so then we need to assume non-zero volume. So then that's yes. That is, we can do that. Yes. So you mean for the R to the D setting? Yeah, that I don't know. I hope it is the case also. Yeah. No, I have actually not thought about that, but maybe. Yes. Yeah.
Additive combinatorics, which is perfect for our workshop.
So good evening to all. I'm very much thankful to Professor Adhikari and the Institute for kind invitation to be among you and discuss something on combinatorics. So let me begin. We talk about a problem in additive combinatorics, as the title says. Professor Stephen Bayer just introduced the sum sets A plus B for where AB could be subsets of any general group G, need not be just integer or real lines and so on and so forth. What I will be talking about is a difference set A minus B. So for given a set A, we just define the difference set to be just A minus A. So just as it says, oh, this slides. Okay. Yeah, thank you. So what we will be talking about, we take a finite group Z for our discussion, finite abelian, and we indicate it with the addition as operation. And for a subset of it, we define the difference set just as like the sum set was defined. All the elements which can be written as difference of two elements from the same set A. So it was, sorry? Okay, yeah. So it was, let me just tell the plan first. So I try to introduce as briefly as possible because problem is very easy and can be understood by anyone. Then we talk about our one main result, which we will discuss at least some pathway towards the problem, and then some requirements for discussing the proof or at least outlining the proof of this theorem. Small results which are part of the main theorem we like to discuss if time and permits, like k equal to 2 and then some more lemmas. So it was Lev who gave a problem on this difference set for a finite abelian group G as follows. So given a difference set, one can write this number of representations of an element as difference. So for given x in this difference set, you may like to count how many times one can write like this. So count ordered pairs AB for which X is the difference of A and B. So depending on the value of this in comparison with the Carnoti of A, it was posed as a problem by Lev that if suppose everybody in different set has at least A by 2 representations, then is it necessarily true that the different set is either a subgroup of G, some subgroup, or at least it's a union of 3 cosets of some subgroup? The problem to state is as is that if you have enough number of representations, say at least half of the size of A for everybody in the different set, it was conjectured that is it always true that A minus A is a subgroup, or else it's a union of 3 cosets, 3 distinct cosets of some subgroup. If you change slightly this inequality to the strict one, like suppose everybody has more than A by 2 representations, one can always show that this is actually a subgroup always. And it's a simple application of pigeonhole principle. As we can see, suppose we have 2 elements X and Y in the different set, and for each one we have more than A by 2 representations as A minus B. Then I can pay attention to the first coordinate, also called the A and B on that side, and I know that they are going to be equal at some point, right? If I just count, if I just pay attention to the first coordinate here, A, there are more than A by 2 such as, because everybody has more than A by 2, strictly bigger than A by 2 representations, and same for Y as well. So I know that for arbitrary X and Y from the different set, we do have A and B to be equal, at least one. And then you take the difference of X and Y, it will be again in the set A minus A. So it's quite clear to see that the different set becomes a subgroup if we have more than A by 2 representations for every element in the different set. But if I take it to be not strict inequality, but as it is said in the equation 1, one cannot expect it to be a subgroup. But then it was conjectured that is it always a union of 3 cosets? And it was given by a simple example by Levin himself, that you take any finite group and suppose an element X I choose such that the coset has at least order say 5, for example. We can take any abelian group and look at the X to be having order at least 5 mod G by H. Then you take A to be this set, namely union of the 2 cosets of H, where H is proper subgroup, some proper subgroup, so that H and X plus H union is our set A. Because it's a union of 2 full cosets, it is straightforward to see that A minus A is a union of these 3 cosets, H, X plus H, and then minus X plus H. Right? I am allowed to take any difference of A and A, right? Because A is a very nice structure, namely union of 2 full cosets, finding the structure of A minus is just straightforward, right? Here you can check that because order of X model H has been taken to be say at least 5, this set A minus A cannot be a subgroup, right? Because order of X is in a way at least 5 in modulo H. If this was a subgroup, your X would have been element of A minus A, and then we should have that 3X would be in H, because index of H would be 3 in this subgroup A minus A, because being the subgroup and union of 3 cosets of H. And that's how we chose X to be having order say like at least 5. So here this is clearly seen to be not a subgroup, because if it were subgroup, as I said, 3X will be in H, but it is a union of 3 cosets. And the Lev conjectured that, or proposed the problem that is this the only case, says this one. So we took this problem long time back and tried to work onto it. So we observed that whenever we take a non-cyclic group, neither of these conclusions can be made to be true. By experiments, we in fact gave an example in the group Z at some Z true, with A H to be that subgroup generated by 4, 0, and A to be the union of those 4 cosets of that H, where purposefully we have not taken the trivial coset in A. We took the cosets given by 1, 0, 2, 0, 3, 0, and the 0, 1. So A is still the union of full cosets of some subgroup H in this case again. But if you work it out explicitly, you found that A minus A becomes union of again the cosets of H, but only 7. Right? So we can just manipulate and work it out. And in this case, because of order of A minus A is say 7 times 2, then it's not a subgroup of G. And secondly, one can check that it is not a union of 3 cosets also of any subgroup. Otherwise, 3 would divide 14, right? So simple observation tells you that if you have a non-cyclic group, it is not even expected. Neither different set could be a subgroup or a union of 3 cosets, even though we have that condition of everybody in A minus A has at least A by 2 representation. Of course, your group is cyclic or not cyclic, the moment you have everybody having more than A by 2 representations, it's always going to be subgroup. That argument is in general. So then we try to pay attention in the cyclic case only because of this example. And this is joint work with Chantal Eshram and Prabal Paul. Let me just state the theorem and then we try to discuss the pieces together. So we could not get again the complete result or the answer affirmative to the problem posed by Lev, but we could give to this extent that you write A as suppose A is given to be a union of, as a union of 4 parts of different cosets. So your A contains x1 plus h1, where h1 is a subset of the subgroup H, some subgroup H. Okay, x2 plus h is again h2 is again a part of one coset of H, but distinct than the previous one. And so you suppose that your set A has been scattered through the 4 cosets of H. We'll come to in a moment to discuss why 4 is the number. But this is a more general and nice looking statement that you set A is contained inside the 4 distinct cosets of some subgroup of H. Okay, it could be any subgroup. For the simplicity of the thing, we assume that these H1, H2, H3, 4, as I said, subsets of H, but corresponds to different cosets as a part of A. And the assumption of that everybody in different set has at least A by 2 representation again, same condition. For the proof to work, which is quite involved, so we try to avoid the cases when this D, the generator of the subgroup H, is a multiple of 4 and 5. In that case, we want all of this exercise not to be congruent mod D by eta. So for example, suppose 3 divides D, in that case, subgroup H is given with the property that 3 is a factor of D. Then we want to avoid the condition that all those exercise becomes same modulo D by 3. So we want this to be happen for even eta equal to 4 and 5 as well. For example, if your group G already has no factor of 4 and 5 in the order, this statement is general. But whenever 4 or 5 are there sitting inside H, subgroup H, then we want this to be avoided. Okay, and the conclusion is still same that in some cases it could be a subgroup, the different set, and in some other cases it is actually a union of exactly 3 cosets of some subgroup. Okay, this is the statement, and we will try to justify why this we are taking A as sitting inside of 4 distinct cosets of a subgroup. So we observe that one of the well-known result in additive combinations is Ruza covering lemma. Using that result, we will see that condition 1 on A, that everybody has that at least A by 2 representations, will force us that A should be sitting inside at most 4 cosets of some subgroup. So A is a part of union of 4 cosets of some H. In our theorem, what we took is that it does intersect every area of these 4 cosets. That's what our main statement involves. We also have the result for when A is sitting inside, say, at most 2 union of 2 different cosets of some H. But 3 is something difficult case, and we could not do anything about it. So as I said, for L equal to 4, our results answer the problem given by Lev. But again, conditionally, because we have to avoid those eta being the factor of D, and in that case, that equation to be avoided. All xi's being congruent, mod D by eta. For L equal to 2, we again have slight condition that because we have only 2 cosets to consider, A is sitting inside union of 2 cosets of some H. We like to avoid this condition that the generator, that x1, x2 element that we took, should not have this condition. 2 either should not divide D, or you say equivalently, I mean, most generally that we want. 2 times x1 minus x2 is not in H. If H is such that, then again for L equal to 2 also we have the affirmative answer, that whenever A sits inside the union of two different cosets avoiding this condition, the conclusion of the problem is still satisfied, that we have union of 3 cosets or subgroup. It will happen that this will be always the union of 3 cosets, but depending on the size of the group, this union of 3 cosets may turn out to be some other subgroup that we will not be able to find out. Okay. So to do this, it is very natural to look at this representative function, our main goal. Like how many times you can write those. So if you we know there is a concept of stabilizer of a subset of a abelian group G, right? You take an element of a group, abelian group, and you translate the set A, x plus A. If it happens to be exactly A again, we call X to be in the element of namely stabilizer element of A, right? So in this case, we want to generalize this. This is already in the literature. We call the symmetric difference of A. What we like is that the element of the group G may not completely transfer the translate of x plus A to be again overlapping with A, but we want to count that it may have some partial common things. And as if I choose delta to be between 0 and 1, say, we want to say that this should be at least delta. So I want the translates of A by X should have at least delta times A elements common with A. So when I put delta equal to 1, because we are in a finite group, this will tell you that the X plus A and A has the same cardinality. That exactly means the stabilizer, right? So we take delta to be between the 0, 1 and define this symmetric set corresponding to the set A, and it's one of the trivial upper bound on this size of this set as A by delta square. Okay, this is true in general group also, but anyway, for finiteness it makes more sense for us. So I will not go into talk about this inequality because it involves something known as additive energy of a set, and then you play around the definition. But it's not hard. It's like you just keep working, it will come. So we assume this is one of our ingredients for our justification that why we like to work only A to be a part of at most 4 cosets. Yeah. So put delta equal to 1/2, then the difference set in our context that we assume that everybody has at least A by 2 representation exactly coincide with this symmetric set. In the case delta equals to 1/2, right? Because you look at just whenever I have an element, say A common in the A and x plus A, the next becomes A minus B, right? If I like that B to be x plus A. So this is natural to think of this symmetric set, and with delta equal to 1, we already have an upper bound on the size of A minus A. Like some set we saw in the previous class, we like to have upper bound, lower bound, and when the bound is tight, we expect some structure. In this case, we have the difference set, and now we know that difference set is of at most 4 times A size, right? This is one of the thing. We like now to recall a lemma due to Ruza, which is known as Ruza covering lemma. It has application in almost in every theorem of additive combinatorics. So what it talks about is that you given 2 subsets of a group G. In this setup, G need not be even finite. This is the general lemma, but we take it for finite thing which we want to work on. So given any 2 subsets A and B of G, what the lemma says that I can cover one of the sets, say B, by translates of difference set, right? So I can find some translates of A minus A, so x many translates, such that B is covered by x many translates of A minus A. That's what it simply says. I can cover one of the given set by the translates of difference of other set, right? And also he has given that x can be chosen to be at most A plus B by A, was it is there. And of course, the last case that I can have translates are distinct. A plus x has same size as A times x. So translates are actually distinct. They are not overlapping. So what we can do is that we put B equals to minus A in this result of Ruza, and we come back to say that the minus A, because if I put B equals to minus A, I do have rightly this one, I need x many translates of A minus A to cover the set minus A. I put B equal to minus A. And in addition, by the same lemma, I know that x is at most A minus A by A size, which is now we know is 4 by previous slide, right? The difference set is at most 4 times A for any A, and therefore, for A where we have that this condition on the number of representations to be at most A by at least A by 2. So I can just combine these and put H equal to, say, for example, the subgroup given by the differences A minus A. That's a some subgroup of G, and I apply look at this, replace minus A, multiply by minus A again on both sides. So this will tell you that I can cover the set A by at most 4 translates, right, of the subgroup H. It's larger, of course, than A minus A in general, but when A minus A happens to be a subgroup, this will be again same. So we cannot improve it further, but we can only say that combining the symmetric set concept and along with this result of Ruza, that set A should always be covered by at most 4 cosets of some subgroup. In this case, we know what the subgroup is, A minus A, right, generated by the differences of A. So that's why we can pay attention to only those subsets of group G where it sits inside at most 4 cosets of some subgroup, right? That justifies this. We start, like, let us recall some notations to discuss the some results. So we will call H to be generated by D and write A as, say, L cosets for general notation, where I write Hi to be the subgroups of H, and I call Xi the generator of that coset we may write, and A becomes the union of those L cosets, parts of the L cosets, right? These Hi's need not be subgroup of H, they are just some subsets of H. Okay, I write explicitly the elements of A because I know that this is inside union of some, say, L cosets. So instead of calling those parts as, say, AI, I write this as Xi plus Hi, where Hi is a subset of some group H. Right, this is obvious, right? I just note the elements. Further, we have a very easy assumption that I can assume that each of these parts of subgroup contains 0 just by translate, right? We also assume that 0 is in every part. In other words, we assume that those x1, x2, x3 or xl's are the elements of A, right? And that is easy observation, but it's quite handy in all the proofs. We just indicate Hi, small hi to be the size of every part Hi. So this is again a small result which is quite elementary, but again we use it quite often. What he says that take a divisor G of D and suppose you have at least G plus 1 cosets like this. Then the condition that we wanted to avoid, namely all the Xi's are in the same congruence class modulo D by G, will not happen, right? Remember, when G is equal to 5 or 4 or 5, we wanted to avoid this condition. But it's an easy step to say that if you have more than G plus 1 cosets, then it's straightforward to check that all of them cannot be same mod D by G, right? If you write each of these, say, Xi's as x0 plus mu I times D by G, right? Then because Xi comes from different cosets, they cannot be same modulo D. And hence, it's straightforward that the mu i's that we wrote here cannot be, same mod D, same modulo G. The moment G divides mu I minus mu j, the corresponding Xi's will become multiples of D, right? And they lie in the coset H, same coset of H. So point is that because L is more than G, we cannot have G plus 1 many congruence classes modulo G, right? So L has to be at most G if they are distinct. So one of the most applied lemma is this one, where we took already A to be the union of full cosets, as those two examples suggest that whenever you become A to be a union of full cosets, we can have a nice structure. We can compute A minus A very easily because just differences of the cosets. So what it says that whenever G divides D, and suppose this time you have at least more than G by 2 cosets in the consideration, but not more than G. So L is between G by 2 strictly bigger than L is bigger than G by 2 strictly, but at most G. And again, A is the union of full cosets. It is not partly partial cosets, okay, subsets of cosets. But then again, we say that the condition that which are troublesome is not possible. Sorry, if this happens, then easily one can show that the difference set is a subgroup. In that subgroup given by D by G. So let me just sketch this proof. So you write each xj as, say, for example, x1 plus mu j d by g. Our assumption is everybody is same mod d by g. So I write them as x1 plus mu j d by g, right? Then you take the difference, and as before, you observe that d cannot divide the difference, right, of xi minus xj, because they have been chosen from distinct cosets. But then it implies that the g cannot divide mu I minus mu j as before, right? So in other terms, this mu I mu j are represent distinct classes modulo G. So what we like to see is that once they are distinct modulo G, I like to see that how many classes mod G the difference represents. Once they are distinct, mu I mu j, I want to look at the difference of them, mu I minus mu j modulo G, of course, and want to see that how many classes modulo G of integers they represent, the differences of mu I. Because they are enough in number, namely they are more than G by 2, it's a observation that the differences represents actually the complete set of residues modulo G. It's like that when you have a set A of a subgroup G of more than G by 2 size, A plus B is a whole of G, right? Just use that intersection is equal to, let me just write that one. That can be said in general also. Look at any subset of finite group G, and suppose you have size of B to be more than half of G, right? Then you can show that B plus B or B minus B both are same is actually at least. So let me write in this form. I want to show that the sum set or the difference set both is actually whole of G, right? So one can take any x from G and just look at the intersection of B with, say, x plus G, for example, x plus B. Look at these two sets, an intersection there, right? So you check that this is equals to, you can take the union and the difference of the size of each of them. B and x plus B have the same size, right? And the union anyway sits inside G. So you will get that the intersection is non-trivial, right? At least one side, because each part is of the size more than half. So that I use it here for, because mu1 to mu G, mu1, mu2, mu3, mu1 are more than G by 2 in size. So their differences obviously cover all the classes, right, modulo G. And using those, I can now work out that you take any element A of G here, and you know that it's going to be congruent to one of such differences, mu I minus mu j mod G, right? Then this implies that you look at A as mu I minus mu j plus k times G for some k integer. And what it says that, now look at the multiples of D by G, arbitrary multiple of D by G, say A times D by G. So you just manipulate and see that A times D by G for arbitrary A, integer A, is actually lies in the difference A I minus AJ. You write it as mu I minus mu j D by G plus k times D for that integer A, and you just manipulate that and get it that it is in this. So recall that we do have assumption on this statement that each of these xi plus h is a union of full coset, right? Each of them is a coset. Had it been part of it, we would have trouble here itself, that how to say that xi minus xj, for example, is in the difference, right? Because this decay is there, so I can assume the xj plus decay is there and xi plus 0, for example. Had it been partial subset of the some coset, we cannot do this. But nevertheless, this is gives an idea that D by G now is in subset of the difference. The other way is obvious, because as I said, A is a union of full cosets of that subgroup. So difference is obviously in the subgroup D by G, right? Each of them is a coset. So when A becomes the union of full cosets, and the condition that all our x's are same mod D by G for some G, it's straightforward to check that A minus A is a subgroup, in fact, given by D by G. So what would be idea is that whenever we do not have one of the part of A to be a full coset, somehow try to force it. The condition, the hypothesis that we have is such that we will try to force each part of this A, namely the part which sits inside one coset, to be larger enough. And then we try to somehow impose this condition that all of xi's are congruent mod D by G for some G. So the case L equal to 2 is, again I said this straightforward. Let me do it. So in this case we have only two cosets given to there which contain the A. So I call as before in the notation, and the condition that 2 does not divide D, or as I said, we need 2 times x1 minus x2 not in H. That's what more precisely we need. So you write this x1 minus x2 in how many ways? Okay, because I have only two parts of the two cosets, and I look at the difference x1 minus x2. So naturally it can come only from A1 minus A2, right? It cannot come from the 2 minus 1 because of our simple hypothesis, right? So x1 minus x2 is a part element in the difference A minus A, and it has only one representation, namely coming from A1 minus A2, right? So that tells you that how many times it can come now. So we can write each element in the difference and see that x1 minus x1, it can a representation of x1 minus x2, and see that I have exactly the number of times as elements common to h1 and h2, right? So you write x as x1 minus x2 as some element, say x1 plus h minus h1, x2 plus h2, where these are the elements from the different parts a1 and a2. So if I have two such expressions to be equal, okay, you can see that this directly tells you that h1 and h2 should come from the same, they are equal, and therefore as many elements that you are common with this h1 h2, the parts of the cosets, that many expressions I can get for the difference, right? Equating these two, I get h1 h2 to be equal, and that exactly says that as many elements are common there, that many representations are possible, right? So but now we have hypothesis that this is at least a by 2. In this case it is h1 plus h2 by 2, and that's at most the intersection. So you use that intersection is at most h1, you get that h2 is smaller than h1, and the other way around also. So we'll get that at first the carnetics of h1 h2 are same, but then because intersection is at least a by 2, you in fact forces that the set h1 h2 are equal, right? That part of the subgroups are actually same. Now then again, as before in the example, what you do is that look at the difference of two elements now. Okay, you take two elements a and b from h1, and again this time look at the expressions for x1 plus a minus x2 plus b, where a, b are some fixed elements to choose, right? We obtain that h1 h2 are same sets. Now we want to show that in fact they are forming a subgroup. So look at the expression x1 plus a minus x2 plus b, where a, b are arbitrary from h1. And as just this before, you obtain that the number of possibilities for this is exactly as same as h1 minus a elements of that being common with h1 minus b, right? But anyway, that is at most h1 because it's the intersection of a subset having carnety at most h1, right? But again, then it becomes sandwich between the two, and you observe that the sets h1 minus a and h1 minus b are equal. That exactly means that by taking the difference, that h1 in fact now becomes a subgroup, right? A minus b lies in h1 for arbitrary and b. But this time we look at the expressions, representations of x1 plus a and x2 plus b to conclude this. So once that is subgroup, it's again, as I said, once they become subgroups, it's easy to compute the difference set. And in this case, we found that a minus a becomes union of these three cosets, obviously, right? x1 minus x2, x2 minus x1, and the zero coset, coset given by the zero element. Yes, they are the only possible differences. So L equal to 2 case was easy to handle that way, but L equal to 4 is much trickier and in fact quite involved. For example, one can observe that look at any typical element. We try to copy the method for L equal to 2 and see where the hurdles, right? So for that we ask, suppose I take I and j to be not equal and look at the difference x minus xj. And I again ask in how many ways I can write this as a difference, because every part of the coset is a coset of a subgroup H, right? If I take difference, of course they are going to be same modulo H. So you ask, for example, choose I and j, and can it come from j minus I? That's one possibility. And you can say that there are three more possibilities with xj minus xr, xj minus xr, and xj minus xs, right? With j as the first choice of element. And there are four more, xr minus xi, xr minus xs, and s minus I and s minus r. There are these 7 possibilities as such, right, for writing an element xi minus xj. coming from different parts of AI AJ, right? I wrote it as modulo D, but that too is what we want to see that among those 7 possibilities, how many can be there, right? Because our assumption is only that this exercise comes from different cosets of H. That's what we would like to exploit. For example, among the 2, 3, and 4 equations, at most one can happen. If there are two equations among the first 3 are suppose holds true, then I can equate the right hand side and get that 2 of the exercise are in same coset of H, which is against the assumption, right? Exercise comes from different cosets. Similarly, the only one of the 5 and 6 can happen, and only one of the 7 and 8 can happen at a time. So in general, we say that for any arbitrary I not equal to j, among those 7s, only one of the first 3, only one of the second 5 and 6, and only one of the 7, 8 can happen. So in all, one may say that xi minus xj can have at most 4 representations. One is from ai minus aj itself, which is not written here. The second other 3 comes from these groups, group of 2, 3, 4, 5, 6, and 7, 8 elements, right? So this, for example, and in fact there is further reduction. Suppose second happens, right? One can have, even from the remaining groups, you can rule out the few more cases, right? Because of the index being same, j and I, and so on. So this leads us to consider the following set. Okay, fix I minus j and just call C xi minus xj as what are the r minus s, r comma s tuples, such that xi minus xj has representation from ar minus as, right? This set will always have at least one cardinality because it should come from ij anyway, right? And if there is no more, then this set is just 1, but there could be possibility of that it could be 2, 3, and in fact 4 also, right? We just saw that. Yes, please. Yeah, just notation, just notation. We have been playing with this is a notation, nothing more. In fact, we can call it Cij, but to make it more emphasized, we write C of xi minus xj. It depends on the difference, not even the index I comma j, right? Order tuple you may say I comma j. So you just ask how many times you can write I minus j and what are the tuples which makes it possible. So we can also and small Cij we call this cardinality of these pairs. So we observe, as I said, that it's at least 1 because ij comes from ai minus aj anyway, and it can come at most from 3 more extra, right, among those equations. So we have this xi minus aj being between 1 and 4. So the idea is that take each of 1 by 1 and try to work it out. So in fact, there are several lemmas which establishes that case by case, the fact that this HIs actually should be equal to some H. All H1, H2, H3, the parts of subgroups which occurs in, as it translates inside A are actually same parts. So that so approach, as I said, is that look at these different cases and somehow force that all the H1, H2, H3 are equal first of all. So achieving it is equal is a more difficult part. Once they are equal, they should be equal to full subgroup H itself is a little easy. But getting that all of HIs, H1, H2, H3, 4, H4 are of the same cardinality is a little difficult. So again, so in many of the proofs where we wanted to show H1, H2, H3 and H4 are of the same size or in fact the same set, so approach is like this. You first get they have the same cardinalities and then try to compare the sum H1, H2, H3, H4 by 2, which is A by 2, with the number of representations for a suitable choice of the element in the difference. Okay. So for example, suppose you know that I and j is such that xi minus xj has only 2 representations. One is ai minus aj and the other one is say from ar minus as. That means that set of order tuple is only 2 for one I comma j. Okay. So for because we are using it so often that we call it as unique representation if it comes only from these 2 cases. Xi minus xj comes from ai minus aj and one more r comma s. These r comma s could again have some I or j common. Okay. But in this case, as in this previous cases, we can look at the difference xi minus xj and try to count how many ways it can come. So it's easy that xi minus xj comes from, as in the previous arguments, it can have hi intersection hj many representations for sure. coming from A1 AI minus AJ, right? This element xi minus j comes from as AI minus AJ this many times in empirical equality. But if you look at the representation in terms of AR minus AS, we can just put, because we do not have any more control, we just say that it is anyway at most the minimum of HRHS. Because if I count A minus B, where A comes from HR and B comes from HS, the AS has to be distinct. Otherwise, representation is same. So I can just put the upper bound as maximum of minimum of both, right? As an upper bound for a representation of xi minus xj from AR minus AS, right? So we have this number. It's lower bounded by the sum of all the 4 by 2 and at most this one. So this is nice sandwiching thing, but there is still a lot more things to do. So idea is that you choose I and j, keep choosing I and j step by step and one by one, depending on the which equation among those group of 7 equation holds true, right? And then see, can you squeeze this? So as I said, once if you have that these H1, H2, H3 are equal, showing that they are equal to a subgroup H itself is easy, and that's taken care of by this lemma. And then there are several lemmas which takes care of that, depending on the size of those R, S pairs representing xi minus xj, which make sure that size are equal. So once they are equal, this lemma can be applied, and we are in a better shape. So let me not. I have some 5 more times. So I am not going to do this lemma, of course, but as I said, these are the 3 different cases of that size of R, S, and run through it. But there is a, so once you have all of them to be equal, say after those series of lemmas, what is next step is that we cannot still apply the lemma 4 as such, where we know that once they are union of A is union of full cosets, only when I know all of the x's are in congruent modulo sum d by z, then only lemma 4 can be applied, right? The lemma 4 was the first or second lemma, which was saying this one. Yes, this one, right? Only when all of them are congruent to mod d by g, not this one, sorry. Yeah, this one. When we know A is a union of full cosets, we can compute the difference set, no problem. But the counting is, I mean, looking at structure of A minus A is easier if all of them are same mod d by g, right? And even though you show that all of h's are equal and equal to a subgroup, still you may not have all of them to be sitting in the same congruence class for some g, right? So to do this, in fact, there are only 2 numbers which are hurdle for this lemma to be applied, and that is taken care of separately. Yes, this one. So for d equal to, so when d is a multiple of 2, we may not have all of the 4 to be same mod d by 2, right? So if they are there, I am in the position to apply the lemma. So we take the case where to devise d, and suppose those 4 x1, x2, x3, x4 get partitioned into 2 classes mod d by 2. And in that case, we work it out and say that the difference set is now union of 3 coset in this case. This union again may become some subgroup that we do not know, but definitely it's a union of 3 cosets, right? And then one more number which is hurdle is number 3, modulo 3. If 3 divides d, then also those 4 elements x1, x2, x3, x4 may get partitioned into 2 classes only. Not all of them may not be equal, mod d by 3. So that also has to be taken separately, and that's what this lemma does. When 6 and 7 divides and all of them are equal, we can apply that lemma directly, and that's what this 13 and 14 lemma codes. So after all of this, which is already quite involved, and step by step one has to go down at least 3 levels down. Among the 7, maybe only 2 equations are true, and with one particular I minus j, you may not squeeze that inequality. So what you do, change your number, so change your element xi minus xj to some other r minus s, and try to push those 2 bounds on the representations to conclude. So at the end, what we have is that A is a union of full cosets, right? And with those many lemmas at the hand, at priori, A minus A is a union of, say, 12 cosets, let us say, because I have 4 cosets, difference can be at most 12, right? 12 cosets. So, but the congruence condition may drop down them. And our aim is to really show that the hypothesis that everybody has at least, say, by 2 representation actually squeeze those cosets. They cannot be distinct, right? And in one of the, in fact, 2 steps, while we try to say that these 12 are not distinct, they can be either a subgroup altogether, or they can be union of only 3 cosets of suitable D by G. We need those 2 conditions to be avoided, that all of them are not same mod D by 4, and all of them are not same D by 5 as well. So that I think I will not go into it. Can I take? Shall I stop or can I continue? I wanted to give this lemma, this at least D by 2 case, when 2 divides D, how the partitioning of the elements mod D by 2 gives you structure of subgroup, 3 cosets of D by 2. But I think I'll stop it here. Yeah. Okay. So plan was to give this lemma L1 where I have x1, x2, and say x3, x4 are in the same class mod D by 2, and then try to show that A minus A is a union of 3 cosets. So here is proof. So now that, where is that? And now that we have all HIs to be equal and equal to H, okay, these 2 things has been already achieved, the most difficult part. And now with the cross, for example, suppose 1 and 3 are same mod D by 2, just for notation purpose, and 2 and 4 are same model D by 2. I have the 2 classes mod D by 2 among the Xi's. So what you write is, I write x3 as say x1 plus mu D by 2, and x4 as x2 plus lambda D by 2 for mu1 lambda integers. But again, we know that x3 and x1 cannot be same modulo D by our choice. So mu and, for example, similar reason lambda cannot be even, right? None of them can be even. So you write further mu as 2 mu dash plus 1 and lambda as 2 lambda dash plus 1, and use this. In fact, we claim that these are the 3 cosets, right? So as I said, once you know that this A to be union of the full cosets, computing A minus is easy. So what we have to work is that reduce it to the number of cosets to be say 3. And in this case, we claim that it's a union of the trivial coset D by 2, then the coset x4 minus x3 given by x4 minus x3, and the other way is x3 minus x4 of D by 2. For example, how to show that D by 2 subgroup sits inside A minus A is that you look at any multiple A of D by 2, A times D by 2. So when 2 divides this non-integer A, it's obvious that this is a part of the subgroup. It's a multiple of D. In the case 2 divides D, and anyway A is inside A1 minus A1, for example. A1 is already some coset, right? So A1 minus A1 is containing the subgroup H, and that's in the part of the difference. If it is not multiple of 2, the integer A is not a multiple of 2, you can write it as 2A dash plus 1, and you just manipulate by writing that A D by 2 as 2A dash plus 1 D by 2. Then you multiply by D on inside, you get A dash D plus mu minus 2 mu dash D by 2, and then use that this expression of x3 is equals to say x1 plus 2 mu dash plus 1 D by 2, right? So we replace this with the difference x3 minus x1 plus a multiple of H, multiple of D, right? So that's anyway part of A minus A because it is in the A3 minus A1, for example, capital A3 minus A1, right? So this is how you show that the whole subgroup D by 2 sits inside the difference. It is larger than that, in fact, by the similar arguments. You show that the coset x3 minus x4 plus D by 2 also sits inside the difference. I think I will not do that because it's more or less similar. And the third coset is this one. Okay. To show the equality of this A minus A being union of these 3 cosets, one has to show that look at all those differences of the sets A1 minus A2, A3 minus A1, and all possibilities. Because of the assumption that 1 and 3 are same mod D by 2 and 2 and 4 are same mod D by 2, one can easily observe these identities, right? The difference is a part of D by 2, and otherwise difference is a part of that coset, and so on and so forth. Okay. So D, when 2 divides D, and this is the case, the proof was little easy, but when D is a multiple of 3 and the x1, x2, x3, x4 sits inside the 2 different classes, then it is a little more involved. But anyway, I have no plan to go into it unless somebody discuss with us. So anyway, these are the references for heat. And anyway, thank you for attention. So I will be happy to discuss or any questions. As per as our knowledge is there, the problem is still unsolved. Right? right? We have only kind of partial answer. Yes, please. Main, okay. You mean the statement of theorem or the problem? You want to go up or go down? Okay. This is our result. You mean in this one, proof of this? After this, okay. This one. So after this is proof of this case. The L equal to 2 case. This one. Okay. Here, yes. Oh, that's assumption. Our assumption of the problem is that everybody has A by 2 representations, right? In this case, A is actually union of those H1, H2, H3, H4. I mean, it's union of X1 plus H1, but it's same as H1 cardinality. So that is the actual assumption, A by 2. Everybody has A by 2 representations. That's our problems hypothesis. What we try to see that we just try to get some good choice of I minus J where this can be squeezed. But yeah, to do this, we were waiting for 1 year to reduce because many referees gave us a comment that try to reduce the computations or so-called cases, but we are helpless. No, it plays, sir, because we are taking the group G to be cyclic group Zn. Yeah. Yeah, that's what. See, that's why once we have a say it's a union of 4 quotients inside 4 quotient of some H, right? Where H is a multiple of D. I mean, subgroup generated by D. So we can work with H itself instead of G, because everything sits inside the subgroup H, right? Differences or the addition of this A or A minus A. So I can just forget the bigger G and work only in H. The equations which are read modulo D or modulo D by 2, when I read D by 2, that time I may have to go. The order of G, yes. Yeah. 3, yeah. That's the beauty of this question, which I also, I introduced me that this 3 union of 3, why should it be only 3? That made us interesting. In fact, this has a history, I think you know it. Yes, Sami. Yes. Okay. Generalization of that stabilizer of a steps. Oh, where is that? Here, yeah. This one? Yes. Oh, delta equals root 2. Okay. This one. Yeah, that is natural because this set, our interest is in the difference A minus A, right? And with the hypothesis that everybody here has at least A by 2 representations. So this is exactly the set we wanted to study, the number of representations, right? This side is exactly the number of representations of X as a difference, A minus A. Maybe I was too fast, but yeah. Delta equal to 1 is what we know stabilizer standard 1, but people have been using for various deltas. And our context, because we are looking at difference, delta equal to half sits perfectly with the hypothesis. Oh, many places. I'm sorry, I could not recall, but yeah, it has been used for general delta. Yeah. Anyway, there are many questions like can you lower bound or upper bound and things like that. This is anyway, though this is trivial bound because it comes just apply the so-called additive energy of a set, right? But we try to improve this. Can we improve? Because if you improve it, but it's a 1 by delta square. So improving will not give any integer. Unless the 4 is best that we can get. So we try to think of that way also. Can we push it say 3 times A? But that's not possible. And anyway, examples are there where 4 times union of 4 cosets, for example. So for our purpose, 4 is the best bound, and that's anyway we want. and we cannot improve further. We were trying hard that can we improve this, or maybe some cases where delta can be taken something nice. In fact, this Leo posed questions for delta equal to 1/2. This question which we have discussed, but he said that for practical application, more interesting applications, he like to see delta to be not 1/2 but little less. Say 1/3, for example. So everybody has 1/3 of A representations. What can you say? So nothing is known. When we contacted him, he said that somebody has done the work, but Gankevich, sir, David Gankevich, but nothing is in the literature. So far as we know. When I was doing postdoc, I was searching some problem, and I could get hold on this and interest. So it's long time thing. Maybe we'll discuss. Yes. Anything? Thank you very much. Sir. Oh, thank you very much, sir. Thank you very much. Thank you very much. Yeah. Thank you very much. Thank you very much, sir. Yeah. Thank you. Oh, feeling too much.